Hello everybody. In this video I want to first talk about what happens if we have columns with various end conditions. And I would do an example right after that for you. So you guys remember that we did the derivation for this case. Actually, this is the case where both ends are pinned. Again, remember that pin doesn't mean that this guy cannot buckle under a compressive load. In fact, all it tells you is about the boundary condition and the fact that the deflection is 0 here and 0 here. So you guys remember that the equation that we got was pi squared EI divided by L squared. So now we're going to modify the equation so it could fit and be used for any other of these conditions that you could see. And I'm going to talk about each one of them in a second. So instead of having the denominator as just L, we're going to make it KL, where KL actually is also known as the effective length. So in the case of if both ends are pinned, as you could see here in this picture, right? If both ends are pinned, the picture keeps moving. The effective length actually is going to be L, as you see here in the picture. All right, I gotta put this back. Okay, in this case, K equal 1. All right, so it would be exactly what we had before. By the way, what is the effective length? The effective length is the distance between two consecutive inflection points. Inflection points, actually in this case, would be this point and the point here. And inflection point is the point where moment would be actually equal to 0. Okay? So now what happens if one end is fixed and one end is free? Okay, so fixed free. In that case, K becomes 2, or the effective length is going to be equal to 2L. All right, so you see, this is an inflection point here, and this is an inflection point right here. Okay, so that would be 2L. So in that case, K would be 2, and then your effective length, by the way, just a quick comparison, if this is 2 and you square that, that becomes 4. So actually a critical load, when you compare it with the pin case, would be 1/4 smaller. So it's in a way 4 times easier to do this than doing this, meaning in terms of buckling. Okay, so you can always make comparison with respect to the pin, which is the one that we did the derivation. Okay, let's keep going. What happens if you have one end fixed, both ends actually fixed, which would be this case? In that case, the effective length actually becomes half of the L, or K becomes 0.5. So you see the two inflection points right there. Okay. Next, actually, now let's make a comparison. If you have 0.5 here, right? What if you have a 0.5 here now in the denominator? And 0.5 is squared becomes 0.25. 1 over 0.25 is 4. So doing this is 4 times more difficult than the pin. So it's 4 times more difficult to buckle a fix. Again, fix, guys, doesn't mean that this guy cannot buckle. It means that both slope and deflection are 0 at both ends of this guy. So deflection and the slopes are 0. All right, and then the last one is, what if one end is pinned, like here, and one end is fixed? In that case, the effective length becomes 0.7 L, or K becomes 0.7. You can make a comparison if you want. All right, let's look at an example here, guys. Very simple example. We have a steel column, a column made of steel. Length is 9 millimeters, fixed at both ends. So that would be this case here, right? So basically your K is equal to 0.5 in that case. Modulus of elasticity is given and the yield is given. Remember, we always have to check to see if buckling happens before the material yields. the cross section of this beam as shown here. So it's an I-beam with the dimensions given in this picture. So we got to basically look at two axes, two major axes, the x-axis, the horizontal axis, and the y-axis. And then remember, guys, our objective is to find the smallest critical load. So you have to go and calculate I sub x and I sub y, and then obviously pick the smaller one. So let's go to the next page. I have, again, this picture here. I sub x, as you have seen before, for the for I-beams can be calculated as shown. So what I did, basically, I thought of this as, you know, one whole rectangle, and then I subtracted kind of these two pieces out of it in one equation. We don't have to use parallel axis equation. And for I sub y, actually, we have two identical flanges. For the flanges, we have this, and for the web, I sub y becomes that. But look, I sub y is smaller than I sub x, right? So we have to use, so this guy will control. So I sub y is going to be used. Remember, in this equation, the critical load equation or the Euler equation, always use the smallest moment of inertia. So go ahead, plug in pi squared E modulus of elasticity I sub y. Remember, k is 0.5, as I mentioned in the last page. Be careful, guys. 0.5 times 9 is 4.5, and then you square it. Okay, this comes out to be a very large number, which is okay, 1300 kilonewtons. Remember, this is a large beam with a large length. 1300 kilonewton or 1.3 meganewton. And then remember, we have to always check against yielding. So I calculated the area here. You can calculate area any way you like by subtracting or adding the flanges to the web. The area of the flange, two flanges to the web. So this is the area. So 1300 or 1.3 meganewtons. I could write this also as 1.3 times 10 to the 6, which is exactly what I have here in a way. Anyway, it's divided by area. This comes out to be about 236.53 megapascal, which is smaller than the yield here. As long as this is smaller than the yield, the critical load that we calculated is okay. So that's going to be the lowest critical load or lowest load that will cause buckling, which means buckling will happen before yielding. Okay? So I'll show you one more example after this video, and that should be it for the course, guys. So for in a way our last week, and then hopefully we'll do a review on that last week, which is just one class. Okay, guys, as always, thank you for watching and listening.